Alright, here's an algebra problem, and this one's kind of tricky, so just sort of bear with me as we work through this. If you actually draw out the diagrams I described, it makes it a lot easier, but I like diagrams are sort of tricky to write out in LaTeX, and I also didn't feel like it, so I don't have it. So, um, I definitely would encourage you to write out what the diagrams look like to help you visualize it. But anyways, so we want to prove that MAM satisfies the universal property of this tensor product, and then prove that these two things are isomorphic. Um, so yeah, so and for what it means for this to satisfy the universal property of this, well, just watch what we do, and then it means exactly what it should mean. Okay, I knew there was going to be typos in here. I immediately see that should be a quotient. But anyways, okay, so we have a universal property of this thing, of this tensor product, such that if you have a map, an A bilinear map from A mod A cross M to N, then there exists a unique A bilinear map F tilde from this tensor product here, such that F is the composition of F tilde with phi here, where here phi is given by, well, you take x comma y and it becomes x tensor with y. So I guess here we don't want an A here, because when we have that A below the tensor product, it's sort of like we're taking the set of x tensor y without anything down here. So we're just taking the set of things of the form x tensor y, and then we're imposing some extra conditions on it, on this tensor product. So basically we use the A as a subscript when we're talking about the tensor product between the two sets, because it's describing the structure on the set itself and not what happens on the individual element level. So I shouldn't have that A there. Alright, so that's two typos so far. Let's see how many other ones we find. Okay, so anyways, so for any F we have this F tilde, we also have this phi. Now to find a map mu from here to here, there's only so many things you could choose. So here's let's take this coset and this element m and just send it to xm plus the xm coset. So to prove it's well defined, if x plus a equals y plus a, then x plus a equals y for some a, and so and I'm sorry when I say a, it's not clear if I mean this capital A or this fancy A. I guess I should have made this R, but my professor likes to use A for commutative rings. I don't know. Hopefully the cursor will point to whatever I mean and it'll be obvious. Anyways, what we have is, well, if we take mu of x plus am, and it's this, but because am is in am, you can write this like this, and then this is precisely ym plus am. So really, all we're really using here is that am is in am. And so that proves that the thing, like, it doesn't matter which coset representative we use in the first coordinate, we'll get the same answer. And so it's well defined. Now to find a new map, f hat, from m mod am to n, by this thing. So we just take it, we put m there, and then we just, in the first coordinate, we just put the one coset. It's well defined because if you choose two different coset representatives and you let am be the thing that makes them like the same, which you can do because they're in the same coset. Then you have, alright, I think I was able to figure this one out. So there exists an AM such that blah blah blah, and then ignore all of this. What we do is we take f hat of m2 plus am. Sorry it's so small, but I'm just happy I was able to figure this out. We can of course replace m2 with m1 plus am. Maybe I would have started with f of m1 and then end with f of m2, or that should be an m2. So yeah, maybe I could have done it a little better, but this will work, so I'm just happy with that. So we get this, and we convert this to f, and then we use a bilinearity of f to split this up into two sums, and then pull this a out front here. And then this we can convert back to f hat and give us f hat of m1 plus am. So we want this thing to be equal to this thing. So we have that, except we also have this extra term here. So what we did was we pulled the a out of the second coordinate here, and then we move it over to the first coordinate to give us a plus a. But that's just 0 plus a because a is in a. But then that's just 0 because we've got a factor of 0 here, so you can pull it out by linearity, and so it's 0. And so in fact we just have f hat of m2 plus am is f hat of m1 plus am, and that's what we wanted. F hat is clearly a, and it's just linear because there's only one argument, so that was kind of dumb, but whatever. So it's linear since f is, you literally just, if you want to prove linearity of f hat, you just, I kind of did that here. You can see how I went from, like, we could have morphed this, like if this wasn't going to die off here, we could have morphed this back into f hat as well, and that would have given us given us linearity. And so I've basically done the proof of that here, if you sort of look at what the structure looks like. Alright, so what else? What happens if we compose f hat with mu? Mu is, of course, this map that's way up here. Okay, let's see what happens. Well, mu of x plus am is going to be xm plus am, so it's f hat of xm plus am, so that's f of 1 plus a, xm. But here, because we know that f is a bilinear, we can bring this factor of x and move it over to the other coordinate here. Here, of course, x is an element of the ring A, I think, right? Where does mu take arguments? Right, yeah, x is going to be in capital A. So anyway, so because of capital A bilinearity, we can do this, but x times 1 plus a is x plus a. Okay, so, oh, hey, look, we ended up with what we started with, and so f of x plus am is equal to f hat of mu x plus am. I guess that's what I was proving, is that this is equal to this composition. Also, now the interesting thing here is that mu is surjective because if you take any element m plus am, then this is just mu of 1 plus am. You could just go from here back to here. And so then, so using this fact, we can prove that, so we have f hat being a map which is bilinear, and this f is f hat composed with mu, and now we can prove uniqueness, because if g hat is another alinear, okay, so here I fixed it, here I didn't have bilinear. If g hat is another alinear map which satisfies all these properties, then one of the properties was it satisfying this equality, and so we have this equation, f is g hat composed with mu, and so what we can do is, given any m plus am, f hat and g hat must agree there, because you just use this composition. You use this equals this equals this. We're using this as well as this in this calculation. But because of surjectivity, we can, every single element of are we using surjectivity here? Maybe we're not using. I think you do have to use surjectivity in some sense because let's see here. So f hat equals g hat on, and f hat and g hat are defined on the same place. It's m mod am. Yeah, I think you do need to be. I think you do need to use surjectivity of the surjectivity of mu. Oh, yeah, of course. We're in this equation here because we can't get from here to here. So we're not just using that mu is surjective. We're using this formula of how to find sort of an inverse image of any element, because that allows us to go from here to here, and likewise it allows us to go from here to here. So we're using this formula here, or this procedure, to get this string of equalities between f hat and g hat. And since this holds for every m plus am, we have f hat equals g hat, and so we have uniqueness. And so what have we proven? We've proven that if we have any a bilinear map f here, and there's a unique a bilinear map f hat, unique a linear map f hat, which is equal to f hat composed with mu. But that's what it means for m mod am to satisfy the universal property of this tensor product. Alright, so all we need now is for this to be isomorphic. And what we're going to do is we're going to use the universal properties of each set, but we're going to replace the map with the one that we were using for the other diagram. And this is a lot clearer if you actually draw out the diagrams, but let's just talk through it. So to prove this thing, let's replace f by mu and n by m mod am in the universal property for the first one. Then there's a unique map, we'll call it mu tilde, because up here we were calling it f tilde, so here we were calling it f tilde when it was related to f, so here because it's related to mu, we're going to call it mu tilde, such that mu is equal to mu tilde composed with phi. So now, if we replace f by phi and n by this tensor product in the universal property for m mod am, then there's a unique, again this should be a linear map mu hat, because again up here we went from f to f hat, so here we're going from mu. No, I think this should be phi hat. It's a unique map phi hat, such that phi is phi hat composed with mu. Then mu hat, or phi hat, these look really awful. Just do that. Then phi hat composed with mu tilde composed with phi is phi hat composed with, well, we know that mu is equal to mu tilde composed with phi, so mu tilde composed with phi we can replace with mu. So now we have phi hat composed with mu, but phi hat composed with mu is phi. So this is this. And again, since phi is surjective, did we talk about that at all? What is phi? Oh, well, of course phi is surjective, because that's how you get elements in this tensor product. It's clearly surjective. Since phi is surjective, we can basically prove that given anything in the image of phi, phi hat composed with mu tilde of that thing is equal to, well, just the thing itself. And so what that means is that phi hat composed with mu tilde is the identity on this set, which means that phi hat and mu tilde are module isomorphisms between these two sets. Module isomorphisms, is that the right thing? Well, yeah. Right? Yeah, because they're being acted on by elements of a... isomorphisms. Whatever type of isomorphism they're supposed to be, they are that. Well, wait, of course, yeah. This whole section is on all of these. All of these are about modules, because M is a module. A mod A is naturally an A module, and M is an A module by definition. And so what we've proven is that these two things are isomorphic, because we have a module, we have an A linear map. Well, wait, is it A linear or A bilinear? V hat. Where is V hat? V hat goes from here to here. Okay, so it's A linear. Yeah, because module isomorphisms are A linear maps, where A is whatever the underlying ring of the ring that's acting on the abelian group is. So yeah, these so V hat and mu tilde are inverses to each other that map between these two things, and they are A linear maps, i.e. they are module isomorphisms. And so yeah, so these two modules are isomorphic, and that's what we wanted to prove, and so now we are done.